Hello class, today we are going to look at complex probability. So we've talked about simple probability, just what is the probability of one thing happening. Today we're going to look at stuff that's a little bit more complicated. All right? So first, compound events. A compound event is a set of outcomes from combinations of actions, such as flipping a coin and rolling a dice, or drawing tiles out of a bag and also spinning a spinner. All right? So doing more than one thing. So let's take a look at this. What is the probability of rolling a 5 on a 6-sided dice and getting red on the spinner? All right? So we've got two things happening. So the way this works, what you do is you take the probability of 5 and red. Okay, we want the probability of both of them happening at the same time. All right, so we have two separate events, roll the dice and spin the spinner. And this little upside down U right here, that means and. All right, so technically it is the intersection of the probability of 5 and the probability of red, but generally just read as and, 5 and red. All right, and the way it works, you take the probability of rolling a 5 on the dice times the probability of getting red on the spinner. So what is the probability of rolling a 5 on a 6-sided dice? Well, it's just 1 out of 6. There's 1 5 and there's 6 numbers, right? What is the probability of getting red on this spinner? Well, 1 out of 5. There's 1 red, 5 different colors. So we have 1 over 6 times 1 over 5, multiply that together, and the probability of getting 5 and red is 1 out of 30, or 3.33%. All right? And just so you can see this, here is the sample space, 5 different ways of getting spinners, and 1 through 6 for the dice. You see we have 30 different possibilities, different outcomes, and only one of them is 5 and red. So here you see we have all of the reds, all of the 5s, and that one where they intersect. Right? Which is why this is an intersection. All right? So let's take a look at another example. You have a bowl of candy. It contains 15 M&Ms, 13 Skittles, and 17 Reese's Pieces because somebody was a jerk and mixed them all up. What is the probability that you pick up a Reese's, put it back, pick up an M&M's, put it back, and then get the Skittles that you were wanting in the first place? All right. Well, probability of two things happening, probability of A and B, or with the little intersection there, is a probability of A times the probability of B. Now we've got three things happening, so it will be the probability of A and B and C. So probability of A times the probability of B times the probability of C. So we want the probability of an M&M times the probability of getting a Reese's times the probability of getting a Skittle. Well, let's see here. Probability is favorable over total, so we do need to know what our total is. So that'd be 15 plus 13 plus 17, which is 45. So probability of M&M is 15 out of 45. Probability of Skittle is 13 out of 45. And then probability of the Reese's is 17 out of 45. Now notice we put the candy back each time because it wasn't the candy we're looking for. So each time it's still out of 45. There's still 45 candies in the bowl until we finally get our Skittle that we're going to eat. And so you just take that, multiply it all together in your calculator, and you end up with 221 out of 6,075, or 3.64%. So in this, since we picked up the candy and then we put it back, the probability didn't change. What you picked up for the second candy did not matter did not care about whatever you picked up for the first candy. Each time it was out of 45. These are called independent events. Whatever you do first does not affect what you do second. Right? You could have picked up 5 Skittles, put them back, and then picked up another Skittle, and it's still the same probability. Doesn't change it because you put it all back. All right? Now, what if instead we picked up a Reese's and we ate it? Then we picked up another Reese's and we ate it. And then we picked up a Skittle. All right? Well, here things are changing because we are eating the candy. And so there's a different amount of candy in the bowl, which changes the probability. These are called dependent events. If whatever you do for the first outcome changes the probability of the second outcome. All right. And since they are dependent events, we cannot use this equation. We get a different equation. And that would be this. So we have the probability of A and B is the probability of A, that's the same. But then we want the probability of B given that A already happened. So this little line right here, that means given. Now we have three things, so we need the probability of A times the probability of B given that A already happened, times the probability of C given that A and B already happened. All right. So let's take a look. We still have 45 candies to start with. So what we have is we have the probability of R and S. All right? So the probability of R times the probability of Reese's, given that we already picked up a Reese's, then the probability of getting a Skittle, given that we've already picked up 2 Reese's. All right? So the probability of getting that first Reese's is we had 17 Reese's out of 45 candies, right? The probability of getting the second Reese's, though, is not 17 out of 45 because we ate it. We ate that first one, and so now there's only 16 Reese's in the bowl and 44 candies total. And then once we eat that, well, there's still 13 Skittles because we haven't eaten a Skittle yet, but there's only 43 candies in the bowl. So we multiply that all together, and our probability of getting a Reese's, and then a Skittle is approximately 4.15%. Right? So if you have dependent events, you have a different formula here. You have to take into account that the first event already happened. All right? Now, another question. In a certain Algebra 2 class of 21 students, 7 of them play basketball, 8 of them play baseball, and there are 11 students who play neither sport. What is the probability that a student chosen randomly from the class plays both basketball and baseball? Well, the question is, which formula are we going to use? Are we going to use the independent events formula, or are we going to use the dependent events formula, right? Well, let's figure this out. Are these independent events, choosing baseball and basketball? Well, it sounds like they're independent. It shouldn't matter if you played one to play the other, but maybe it does. Who knows? So what we're going to do is we're going to take this and we're going to put this into a table, like so. So we'll list they play baseball or they don't play baseball. They play basketball, they don't play basketball, and then we'll have totals on the edges here. So we know we have a total of 21 students. We know 7 of them play basketball. We don't know if they play baseball or not. We know that 8 of them play baseball. We don't know if they play basketball or not. And we know that 11 of them don't play anything. Now what we're going to do is we're going to fill in the rest of this table. All right. So let's see here. I know I have a total of 21 people. 8 of them play baseball, so 21 minus 8 is 13 of them that don't play baseball. 21 minus 7 that play basketball gives me 14 that do not play basketball. And let's see here. We have 13 that don't play baseball. 11 of those also don't play basketball, which means 2 of them do play basketball. And let's see here, that do not play basketball, we have 14 people. 11 of them also don't play baseball, so 14 minus 11 is 3 that play baseball but don't play basketball. And let's see here, we have 8 total that play baseball. 3 of them don't play basketball, which means the other 5 must play both. So now I know how many play both. So are these independent or dependent events? Well, there is a formula that lets us know. That is this. Independent probability. If the probability of B given A is the same as the probability of B, whether or not A happened, don't care, then A and B are independent. One of them doesn't affect the other. So let's see if these are dependent or independent. So we want to know the probability that they play both basketball and baseball. So we want to know, is the probability of basketball given baseball, given that they play basketball, the same as the probability that they play baseball? Well, let's see here. Baseball, given that they already play basketball. So we're only looking in this column right here. So what we have is, of the 7 people that play basketball, 5 of them play baseball, so 5 out of 7. Well, what's the probability that they play baseball just out of everybody? Well, that would be 5 playing, nope, baseball is all the way over here. All of the baseball is 8 people total play baseball out of the total people in the class, which is 21. All right, so those are different. And if they're different, that means it's dependent. You wouldn't think that, right? You would think that whether you play baseball has nothing to do with whether you play basketball. But apparently, for these kids, it does. Yeah, because they're athletes, and so they're more likely to play another sport than people who don't play a sport at all, right? So they're different, which means we want to use this formula, the dependent one. So B given A. Basketball times the probability of baseball given that they play basketball. So that'll be 7 out of 21. It's the probability they play basketball. All of the basket people is 7 people out of 21 people, times the probability they play baseball given that they play basketball. So of these 7 that play basketball, how many of them play baseball? Right. And then we multiply that together, and we end up with 5 out of 21, or 23.81%. Now, I want to point something out to you. We've got this table, right? And we can use this table to tell if they are dependent or independent, if these proportions are the same. But really, if I'm just wanting to know what's the probability of basketball and baseball, well, I could just look to see basketball is right there, baseball is right there, and they intersect. Remember, that's what this little upside down U means. It means intersect. They intersect right here at the 5. 5 out of everybody, 5 out of 21. So honestly, we can do this kind of with skipping whether or not they are dependent or independent, and we can just fill out the table and say, which box do I want out of the total? That's one way to do it. I'll admit, it shortcuts it a little bit. All right, so let's take a look at the next example. On this one, a group of high school students took a standardized test. The number of students who passed or failed the exam is broken down by gender in the following table. Determine whether gender and passing the test are independent. All right, so I put the little rule up here, independent probability, if B given A is the same as the probability of B by itself. All right. So does it matter what gender you are? Do you have the same probability of passing the test? All right. Is it independent or dependent? Does it matter? Well, to do this, we need to fill out the table. We need to know the totals. So total number of males, total number of females, total number who passed, total number who failed, and the final total. And let's just add it up. That's all you got to do. Add across, add down, and then add up your columns at the end. All right. So what is the probability that somebody was male given that they passed the test, right? B given A. Well, so that means we're only looking in the passed column. So passed, that's a total of 156 people. 60 of them were male. So 60 out of 156 people who passed the test were male. All right. And let's go ahead and change it to a decimal because it's easier to compare if they are the same or not. And then what is the probability that they were male that took the test? All right. So the total number of guys who took the test. Well, that would be 95 guys took the test out of 247 people. So 95 out of 247, which is, and look at that, the decimals come out the same. This is independent, right? Which makes sense. It doesn't matter if you're a boy or a girl, you've got the same chance of passing the test. Right? That's what that means. So you can tell independent or dependent if they're the same. They're independent. If it's different, then it depends. All right. Now, we're going to do one other thing. Going back to the original question, which is rolling a 5 on a 6-sided dice and getting a red on the spinner. But what if I want one or the other? I don't care which one as long as you get a 5 or a red. Doesn't matter as long as you get one of them. All right. Well, let's think about this. So, probability of getting 5. One way to do that. 1 out of 6, right? Probability of getting red. 1 out of 5. So, what we have here. here's our sample space. In the total sample space, we have 6 of them that are red. We have 5 of them that are 5s, right? The thing is, though, I just want one or the other. Notice this one right here. The 5 and red, that is in both sections, isn't it? Which means if I just count it this way and I count those, I'm counting this 5 in red twice. So what we're going to do is we're going to take the probability of rolling a 5, 1 out of 6, probability of getting red, 1 out of 5, and then we need to take out this double counting, all right, which is the probability of both. So what this is, the probability of 5 plus the probability of red minus the probability of 5 and red. Now notice my symbol here. I want probability of 5 or red, and my symbol is this U right here. All right, this is the union. It's overlap. Not overlap, it's just all of it together. How much is it together? So let's see, we need to add these fractions together, so we need common denominator, which would just be 30. So 5/30 plus 6 out of 30 minus the 1 overlap. 5 plus 6 is 11, minus 1 is 10. So the union, or probability of 5 or red, is 10 out of 30, which is 1/3, or 33.3%. And what we can do, we can generalize this equation right here, like so. The probability of A or B happening is, and here it is just with the symbol, so you remember that symbol is that's or, right? Or the probability is the probability of A plus the probability of B, not times, plus the probability of B minus the overlap, probability of A and B, right? So let's do an example here. In an Algebra 2 class of 22 students, 5 of them play football, 11 of them play baseball. There are 3 students who play both sports. What is the probability that a student chosen randomly from the class plays football or baseball? Okay, not and baseball, or baseball. All right, so here's our formula. Probability of A or B is the probability of A plus the probability of B minus the probability of A and B. All right, so let's see, we'll let A be football and B be baseball. So with the probability that they play football plus the probability of baseball minus the probability of both. Let's see, football was 5 out of how many students? 22. Baseball was 11 out of 22. And does it tell me how many play both? Yeah, 3 of them play both. So we have 5 20-seconds plus 11 20-seconds minus 3 20-seconds. So 5 plus 11 is 16 minus 3 is 13 out of 22. All right. Fairly simple stuff. Well, this one was simple because it told me what the overlap was, right? So let's do one where it doesn't tell me what the overlap is. So here, 20 students, 12 of them are in band, 13 of them are in athletics, and there are 3 students who aren't involved in either band or athletics, all right? So we have the probability of A or B, all right? Now notice though, it told me how many aren't involved in either. Now I don't want how many aren't involved in either. I want how many are involved in both. I need to know what the overlap is, right? Probability of band plus the probability of athletics minus the probability of both. So what we're going to do is we're going to make a table so we can figure this out. All right. So here we go. And how many are in band or not in band, in athletics, not in athletics, and then totals on the side. So the total in athletics is 13. The total in band is 12. 20 total students in the class, and 3 of them that don't do band or athletics because they do something else. Maybe they're in ag. I don't know. Anyways, so let's see here. We've got 20 students. 12 of them are in band, which means 20 minus 12. 8 of them are not in band. All right. Of those 8 that are not in band, I know 3 of them are not in athletics, which means the other ones are. So 8 minus 3 is 5. Let's see here.
Oh, you're videoing. My bad.
So, 20 of them total in the class, 13 in athletics, which means how many are not in athletics? Well, 20 minus 13 is 7. Of those 7 who are not in athletics, I know 3 of them are not in band, which means the rest of them are in band. So 7 minus 3 is 4. 12 people in band, 4 that are not in athletics, means the rest are in athletics. So 12 minus 4 is 8. And this is what I was looking for, right? I need the overlap where the B and A, band and athletics overlaps is 8. So now I can fill this in. So the probability of band was 12 out of 20. Probability of athletics was 13 out of 20. And now I know the probability of both is 8 out of 20. So 12 plus 13 minus 8 is 17. So the probability of band or athletics is 17 out of 20, or 85%. Now, I do want to point something out. If they are involved in band or athletics, that means what we're looking for is everybody except these 3 right here, right? We want everybody except the ones who don't do either of them, right? So what we could do, another way we could shortcut this is, remember, we could find the complement. We want the ones that are not in neither one. So probability that they're not would be 3 out of 20 is the probability that they do neither. And so all we got to do is 1 minus 3/20, which would be 17/20. All right. So a little shortcut, another way you could do that. All right. So to review, compound events means you're doing more than one thing. You're flipping a coin, rolling a dice, or it could just be rolling 2 dice, or the ever popular picking 3 marbles out of a bag. That's 3 different things. All right. If they are independent events, then the probability of one has nothing to do with the probability of the other, like the dice and the spinner. They have nothing to do with each other. Rolling 1 dice and rolling a second dice has nothing to do with each other. All right. If they are independent events, though, then the probability of both things happening, A and B, is the probability of A times the probability of B. All right. If they are dependent events, then the probability of A times B is the probability of A times the probability of B, given that A already happened. So here, when we are eating the candy and not putting it back, that changes the probability. So these are dependent events. And so you have to take into account the fact that you ate the candy, and so there's less candy in the bowl when you draw out the second piece of candy. All right. If the probability of A given that B already happened is the same as the probability of A, if these two are the same, then they are independent events, like it was with passing the test based on gender. Independent, doesn't matter. But if they are different probabilities, that means that they are dependent. Right? And finally, if it wants A or B, you add, you do not multiply. If it's A and B, you multiply. A or B, you add. But remember, you do have to take out that overlap. All right? All right. So, hopefully you found that useful, and I will see you in the next video.